Thanks for the invitation. It's really great to be here. And yeah, I would talk about my recent joint work with Roger Cassels, Ian Lay, and Melissa Sherman-Bennett on T-shift of the reduced paper graphs and Legendrian weaves. So here's the plan of my talk. I'm going to first give an overview of what this project is about, and then I'm going to spend some time to just remind us what Positroid strata are and how to use reduced paper graph to give the cluster structure. And then I will switch gear and talk about Legendrian weaves, which is a bit newer. It came out in 2020 by the work of Roger Cassels and Eric Zaslow. And it's actually really great combinatorial tool to capture cluster structure. So we'll talk a little bit about that. And then lastly, we're going to combine the two together, combine the two known combinatorial gadgets together, and talk about how you actually build the Legendrian weaves from reduced paper graphs and some of the implications of this construction. Okay, so let's start. So overview. So Positroid strata are subvarieties inside Grassmannian. So it was first introduced by Positroid, and then Donaldson, Lamb, and Speyer they made it algebraic. So now they're actually algebraic subvarieties. And they're interesting objects to study from both a viewpoint of representation theory and also from mathematical physics. All right, let's continue. Thanks. Oops, why is it not clicking? Okay. All right. Oh. All right. So a special feature on Positroid strata is that they have cluster structure. So this has been proven in 2019. By Grassmannian and Lamb, and also our collaborators, Melissa Sherman-Bennett and her collaborators, and typically you can capture this by this kind of plabic graph. Plabic stands for bicolor planar. However, one not so ideal situation is that the mutations that you can do on plabic graphs are only the square moves. So whenever you see a square like this, you can do a mutation, but for faces that are not square, then you're kind of stuck. You cannot do the mutation using this kind of combinatorial gadget. On the other hand, Cassels also they introduced this Legendrian weaves, and in following works has been developing this technique. And now we have this new combinatorial tool available to us, and it gives a very explicit connection between cluster structures and geometry. So the initial goal of this project is to relate these two constructions together and see if we can give a more geometric way of understanding the cluster structure on Positroid strata. As an application, this is a bit kind of like a byproduct from our project. We've actually we're able to prove that the equality between the Muller-Speyer twist map on Positroid strata and the Donaldson-Thomas transformation. Okay, so let's start. So what are Positroid strata? So first I need to define what a positroid is. So you consider this real Grassmannian for now, Mn, so you can think of this as you take an m by n. So I would take m less than or equal to n. So you're going to get this rectangular matrix like this, and then quotient out by gel m action on the left. And you should really think of this as taking the row vectors of this matrix and take the span of it. That gives you the m-dimensional subspace in Rn. Right, for example, something like this. Right, so you have 3 by 6. Right, you take the row vectors and take their span, and that gives you the 3-dimensional subspace inside R6. So for any m element subset, you can define a Brooker coordinate to be the determinant of a submatrix formed by the column vectors indexed by I. So for example, I can take the second, third, and fifth column, and I can define a Brooker coordinate 2, 3, 5 to be the determinant of this. Okay. So the total in non-negative Grassmannian, so I have this greater or equal 0 sign above. That means that I'm going to take the subspace where all the Brookers can be simultaneously non-negative. Okay. Alternatively, let me point out that you can also just take the greater equal 0 condition, then you mod out by the general linear transformation with positive determinant. Right. So now, so what's a positroid? So for any collection, so I'm going to denote this by denote the m element subsets of this n element set by this notation. So n choose m with a little bracket there. So if you take any subset of such m element sets, sorry, you take a set of m element sets, you can define this subset inside the Grassmannian such that the Pruckers are non-vanishing if and only if they're inside a subset. And a positroid is such a collection such that this subset inside the Grassmannian is now empty. It's the one that's meaningful. Because a lot of times if you just randomly pick things, then you're going to get an empty set inside. So you don't want that, right? And if you actually get something, it's called positroid. So by positroid, it's a kind of special kind of matroid. Any questions so far for this definition? All right, so positroids actually can be captured by some equivalent things, and one of them is this Grassmann necklace. So let me tell you what a Grassmann necklace is. So you take for each I, you fix an I inside n, then you can find a linear order on n. So I is the smallest one, and I minus 1 is the biggest one, right? So you can, so originally you can think of this as in a circle, and then you break the circle up at some point, and then you unwrap it, give you a linear order. And this linear order will induce a lexicographical partial order on the m element sets. How? Well, so say take 1, 4, 5, and 3, 5, 6, right? And let's try to compare them less than 2. So what you do is you first order the elements inside each subset according to this order. So for example here, right, 4 is less than 5 less than 1, because 2 is the smallest, 1 is the biggest. So you first order the things inside each set, and then you compare the things that are in the same slot. Right? So for example, you compare them, you see that 4 is greater than 3, 5 is equal to 5, and 1 is greater than 6. So it tells you that this 4, 5, 1 set is greater than 3, 5, 6 set. Okay, so it's a partial order, not necessarily. So if any two sets, you may not be able to compare them, but if you do, you're going to get a partial order. Right? So now if you take a positroid, then for each I, there's a unique minimum element, I sub I in P, respect to this partial order. This has been proven by Positroid in his early work. And this sequence of collections called the target Grassmann necklace. So in other words, the positroid is actually uniquely determined by this kind of minimum, the n many minimal elements with respect to each partial order. Okay, so now I can finally talk about the algebraic thing. So the positroid stratum for each positroid is defined to be the following subvariety. Okay, so you take the affine cone of the Grassmannian. So you actually define it without the affine cone, but just because I want to make the Pruckers into cluster coordinates into actual functions, I want to take the affine cone, and I require that if the collection is not, if this index set is not in the positroid, I want the Prucker to be 0. But in addition to that, I also want the things in the Grassmann necklace to be non-zero. Okay, so that's the positroid stratum. Okay, so you should think of this as frozen coordinates for cluster people, right? So you want the frozen to be non-zero. Okay, so given the Grassmann necklace, you can actually draw a link. So I would say Legendrian link here, but this is not important because this is not a symmetric geometry conference. So sorry, symplectic geometry conference. So let's not worry too much about what Legendrian means. But there's a footnote here, probably it's too small for you to see, and it's on purpose, I think. Don't worry about it. But let me tell you how you get a link. So you list the elements with respect to list each this Grassmann necklace entry with respect to this less than I ordering, and then you connect the corresponding elements in I and I plus 1, and then you connect the remaining one. So let me give you an example. So this is a Grassmann necklace. Okay, so you order them each of them with respect to the less than I order. So 1, 2, 3, 4, 2, 3, 4, 6, 3, 4, 6, 2, 4, 6, 1, 2. Right, so this is less than 4, less than 5. So you see that less than 5 actually starts with 6 because 5 is actually missing, and that's okay. Okay, so I sub 5 may not start with 5, it starts with 6, but that's fine. And then for between every two consecutive ones, you just connect the same things together, and there's one thing that's different, and you connect them to the different ones. Okay, and in particular, I want the index to take index mod n, so the first one also comes in the n, and then I will do the same crossing as well. Okay, and after you draw this pattern, and all the crossings are going to be this kind of overcrossing, so you only take one kind of crossing. So after you draw this pattern, you can forget about the Grassmann necklace, and you wrap around the cylinder. So you glue this side to this side, and that gives you a link. And we call it the Positroid link. So yeah, so n is 7, m is 4. Right, so that's how you get a link. So you call it the Positroid link. Okay, so another way you can index positroids is by bounded affine permutations. And the way you get a bounded affine permutation, as we see from last example, between the two consecutive Grassmann necklace entries, only one thing differ, right? Well, possibly one thing differ. So I'm going to define the fp of I to be, so if I is in I, but not in I plus 1, then that means I replace I by some j. And if j is bigger than I, I'm just going to define to be j. And if j is less than I, then I'm going to define to be j plus n. Okay, so I always want my affine permutation to increase. It's always an increasing function. And if I is not in I, then just define it to be I. Right, so another way you can think of this bounded affine permutation is that you can start with a matrix representative, start with some column, and then you try to start with the next column and then search for the columns such that the span of these columns contain this one. So for example, I start with this one. So I want to know the image of this I, right? So what I do is I'm going to start with this column. I'm going to take the next one, until I finally find something whose span contains this one. So in this case, right, this is 5. Right, if I wrap around, I notice that when I get to the second column, I finally get the span of these matrices to contain this, span of these columns to contain this vector. So I'm going to define f5 to be 2 plus 6. So we always want it to increase. So it's 8.
So I sub n plus 1 would be I1.
I sub n plus 1 will be I1. That's right. You always take index mod n. Yes. Thank you. Right. So the theorem of Positroid saying that the positroids, the Grassmann necklace, and the bounded affine permutations are all in bijection with each other. In particular, you can work out the rank of the positroid by taking the average of this difference. So this
What is the bounded affine? We explain how to get one from a positroid,
right?
From the Grassmann.
So it's a map from Z to Z that's periodic and increasing, and that's about it. Non-decreasing, periodic.
What is bounded?
Bounded means, it's periodic, so it's bounded by, so the increase is at most n, I think. Right. Right. Yeah. Sorry, I hit a lot of details because limited time.
That's this periodicity thing.
Yeah, the bound is a periodicity. Affine means it's a Z to Z bijection. Okay. And in particular, if you want to take the top dimensional stratum, it just I goes to I plus m. Okay, so now let's talk about reduced plabic graphs. So each positroid stratum has a cluster A structure on it, and initial C can be constructed from a reduced plabic graph. So plabic graph is a planar bicolor graph with vertices, two kinds of vertices. So normally people call it black and white, but then I'm going to use color later on, so I'm not going to call them solid and empty for the shape that they are. Right, so these are solid vertices, that's empty vertex. I also want external edges to connect to boundary mark points, and we label the external edges by 1 to n in a clockwise direction. Right, so by following rule of road, you can actually draw what's called a zigzag along edges. So what you do is you travel along edges and you turn to the counterclockwise first one at a solid vertex and turn to the clockwise first one at a white vertex. For example, I come in at 2 and then turn here and then turn again. Turn here and then turn here. I get to 1. So that's this zigzag here. And if I start with 3, I'm going to turn here and turn here and then turn here. I get to 5. Okay. So I would say that the plabic graph is reduced if the zigzags do not form loops, self-intersection, or parallel bygone. So if you don't see this kind of things like here, you do not have those, then this plabic graph is reduced. Okay. So reduced plabic graph is said to be associated with the positroid P if the zigzags in the graph goes from I to f of I, where f is the bounded affine permutation mod n, right, for each I. So for here, right, you can read off the bounded affine permutation. 5 goes to 3, 3 goes to 5, and so on. Any question about this? Yes.
Graphs back to so if you start with a pattern of these lines that you formed, and then go back to the original graph you started with.
So if you say you're asking if you just know the zigzags, can you construct a graph? So this is not a bijection. There are many reduced plabic graphs corresponding to the same positroid, and they are all related by square moves. Okay, so thanks for the question. Yeah, so
What are the moves in the language of the cluster structure?
So when you see a square face with like opposite color vertices, then you can change it to the other color pattern, and that's like the only mutation you're allowed to do on reduced plabic graphs. Okay, so how do you construct the initial cluster seed? Well, so for each face, you can actually associate an index set by taking the face. So here I take this one, and then look at all the zigzags where this face lies on the left side of the zigzag. So this is also by convention, right? I know different people have different convention. The convention I go with is lying on the left side of the zigzag. I'm also going to take, and then I'm going to index it by the target of the zigzag. So in this face, I have 2, I have 4, and I have 3. So it's indexed by 2, 3, 4. Okay, so it's called a target labeling. Right, and can complete it. Right, I can do it for every face. I get this pattern here, and then so these are going to be the cluster variables. What are the arrows? So the arrows are drawn such that they form counterclockwise cycles around black vertices. Right, so you can go here and go there. So that's the quiver you're going to get. Right, so I've written a JavaScript program that you can actually generate a plabic graph for together with the Bruker coordinates and the arrows for positroids. If I have time, I can come back and show you how it works later. Yeah, you can also find it on my personal website. So just Google my name and it's an UC Davis server. All right, so second topic, Legendrian weaves. Right. Before we move on, any question for the positroid part? It's a special family of plabic graphs that came from Lie diagram. Yeah, it's just one like convenient way of producing a plabic graph.
The Lie diagram has a single plus like somewhere, or they can have many pluses.
It can have many pluses, but then it's satisfied that if you have a plus here, then there must be a plus here. It's some combinatorial rule. Okay, so Legendrian weaves. So what are Legendrian weaves? So Legendrian weaves is a graph typically drawn on this, but you can also replace it by some other surfaces with color edges and special vertices. And what you're trying to describe is the singular locus of a certain immersed surface in R3. There's a generic M to 1 cover, right? So the M matches up with the M weave here. Sometimes I'll call it the M weave to know that it's an M to 1 cover. So what I mean by that, so here it's going to be a 4-to-1 cover, right? And if you see an edge here with color blue, right? So the color of the edges corresponding to Coxeter's set of generators, right? So it's going to be S1 to Sm-1, right? So it's a 4 weave. So the biggest one is S3. So I'm going to just call this color S3. And what it tells you is that the top 2 sheets cross each other along that pre-image. Okay? Versus if I see a red one, which by convention I call it S2, then the middle 2 sheets cross. Right? And so on. So these are the edges. What about vertices? So there are only 3 types of vertices allowed. One type is this trivalent monochromatic vertex. And what it's trying to tell you is this kind of surface here. So you see, so if you pull out your graphing calculator and graph the image of 3 halves of a complex number, right, and then graph it, right, you're going to see some surface like this. And it's a multi-value function. So generically, you're going to see 2 pre-images, but then along 3 lines, you're going to get a single image, and they just cross each other, right? And also at the origin, the tangent is flat, right? The tangent is 0. So you can also compute derivative and see that. The second type of vertex is a hexavalent vertex, right? So this corresponds to the Bray relation, 1, 2, 1 goes to 2, 1, 2. Right, so you see that it's 1, 2, 1, 2, well, depending on your m, right? So, and what it's trying to describe is this situation. So imagine a 3 coordinate hyperplanes in R3, and then imagine yourself looking down from the positive quadrant towards the origin, sorry, positive octant towards the origin. Then you see that generically you see 3 sheets. But then along the coordinate axis, you only see 2, right? So for example, here you have the top 2 sheets cross, and here you have the bottom 2 sheets cross. So they correspond to this pattern here. Okay, so that's the hexavalent vertex. And then the last kind is this kind of 4-valent vertex that's not really interesting. It's S1 and S3, and they're far away. So you see 2 sheets cross down here, and 2 other sheets crossing up here, right? So they are not talking to each other, and that's all the vertices that are allowed. Any questions? All right. So now I'm going to start with this immersed surface in R3, and what I'm going to do, I'm going to take a cotangent lift. So let me use x1, x2 to be the coordinate on the base, and then z to be the height function, and I'm going to take partial derivatives with respect to x1, x2, and call it the y sub I. And if I just take this lift and then forget about z, then we'll get a Lagrangian surface inside R4 with x1, x2, y1, y2. So I'm using the typical symplectic form here. In particular, this surface is diffeomorphic to the m-fold spectral cover of the base. If you know what this is, it's great. If you don't worry about it. Okay, so what else? What other information can we get from the weave? So you can actually compute the Euler characteristic pretty easily. So the Euler characteristic is given by m, which is the number of sheets, minus the number of trivalent vertices, and that's the Euler characteristic. So once you have this surface, right, you can count the number of boundary components by looking at the external weave lines, and then you know the Euler characteristic, then you know the genus. Right? It's an orientable surface. The Euler characteristic is determined by the boundary components and the genus. Right? So this is one way to compute genus as well. Moreover, we can also depict certain one cycles on this Lagrangian surface by using edges in the weave. How? Okay, so imagine you have an edge here. Note that along this edge, like 2 sheets cross. So when you take the derivative, you're going to get 2 preimages. Right? You get 2 preimages for each point on the edge. So in the preimage of this edge, you're going to see 2 parallel lines, or parallel, right? So you're going to see 2 curves on the exact Lagrangian surface. But then if you see a trivalent vertex at the end, right? So remember the trivalent vertex, the tangent is 0. So the two preimages will meet up along the preimage of the trivalent vertex, and that gives you a cycle on the surface. So an edge connecting trivalent vertices gives you a cycle on the surface. But what about the hexavalent vertex? So at a hexavalent vertex, you could have two typical behaviors. So one is that you can just go straight through, and that correspond to traveling along one sheet and then coming back along the other sheet. Okay, so that's one behavior. Another one is a branching behavior, right? So you can branch off like that, and they correspond to just going here along the vertical sheet, then coming down along the other vertical sheet, and then going this way along the horizontal sheet. Okay. So you could have these two kind of behaviors. Okay, so now I have an oriented surface. I have cycles on them, so I can take intersection pairings between the cycles. And then you can actually compute intersection pairing by using the weave as well. So at a trivalent vertex, if you see the cycles ending here, then you can take the intersection, and the intersections can be given by this arrow, right? So this cycle is going to intersect once with this cycle intersect once with this, and this intersect once with this. In particular, I'm taking a sign intersection, so the arrow actually means something, right? If you take the other way, you get a -1. Versus at a hexavalent vertex, right? The only thing that will give you contribution is the one that going straight through, and this one intersect once with this intersect once with this, and this intersects once with this, and that's it. Right? Okay, so now I can lay down the framework for how you use weaves to describe a cluster ensemble structure. So here's the dictionary. So the cluster seeds correspond to Legendrian weaves. The quiver of the vertices correspond to this kind of cycles on the weave. The arrows are intersection pairing between these cycles. The X torus, you can interpret it as a rank 1 local system on the surface. The X variables are monodromies. For the A side, it's a bit harder. You have to do some work, right? You have to decorate the local system. So what decoration means is you just put trivialization along the boundary of your surface. And the A variables, right? So remember, A and X are supposed to be dual to each other. So if X are given by cycles, then A's are going to be given by the Poincare duals of these cycles. If you take relative cycles, right? And then you can use the trivialization to parallel transport one trivialization to another one and take a ratio. So that's how you take A variables. So the A variables are parallel transports along relative one cycles that are Poincare dual to the X cycles. Right. So in my paper with Roger, we called it the merodromy. Mero means partly, not a monodromy, it's a merodromy. Okay. And what's a cluster mutation? Well, cluster mutation can be done using what's called Positroid surgery. Okay. Positroid surgery is some surgery on exact Lagrangian surfaces that we'll not have time to talk about. But pictorially, it is just taking an edge like this and then changing to an edge like this. That's a Positroid surgery. Okay, so following the work of Casal-Zaslow, the rank 1 local system can be described as certain flag moduli on the base, right? So the rank 1 local, so it's also following the principle of this spectral cover story. So rank M system at the base can be lifted to a rank 1 system on the cover. Okay. So I'm going to so next time I'm going to give you an example. But let me also point out that it's also so we also proved in our joint work that if you have a cycle that's given by a tree, they can always make it into this kind of short edge and then do the mutation, right? So in other words, Legendrian weaves are very flexible, as it doesn't require like this kind of square. This short edge is like a square move, but it's better than that. If it's not a square, as long as it's a tree, you can always make it into a square and then do the mutation. So in other words, this is very flexible gadget. Okay, so let me give you an example. So I'm going to follow Alfredo's precedence and just give the A2 example. So this is going to be a weave describing the A2 cluster ensemble, right? So you have two vertices corresponding to these two cycles, right? And then you intersect them, right? The intersection form is 1. And what about the torus? Well, the torus, the lower local system, can be described by these flags, right? In particular, when you see an edge, a weave edge, that means that the flags differ along that dimension. So here there's only a two weaves, there's only one non-trivial dimension, right? So that means that these two flags, which are lines, right? So it's lines in C2, right? They differ along the, so these two lines are distinct, these two lines are distinct, these two lines are distinct, these two lines are distinct. But also because of these two weave lines, these two lines have to be distinct as well, and these two has to be distinct as well. And that recovers your typical A2 cluster variety. There's one color. There's two weaves, one color. So you're looking at S2 with one single cluster generator. So these are the two cycles on your surface. So you have so you can compute the Euler characteristic. You get a one boundary torus. So one boundary torus has two generators and the intersection once. Because they correspond to quiver vertices and x variables. So the cycle corresponds to x variables. And then if you want the a variables, you need to take the Poincare dual and take monovarojories along those. Okay, so now let's get to talk about how to build the Legendrian weaves from reduced plabic graphs. Okay, so the story started with the joint work of Parisi, Sherman, Bennett, and Williams, and they were studying m equals 2 amplituhedron, and they developed a procedure that will give you a new reduced plabic graph from an old one with one lower rank, and we call this procedure T shift. So in their paper, they call it the T duality, but we realized that that was probably not very good because there's T duality in mirror symmetry, and we don't want to confuse that, so we change it to T shift. And the procedure is the following. So first, make sure that all the solid vertices in your graph are trivalent. If it's not, do this expansion shrinking move to make it trivalent. And if you have a two-valent, delete it. Okay? So make all the solid vertices trivalent. Put the new empty vertex. So I'm going to give you an example here to just guide you through. So first, make sure that all solid vertices are trivalent, which already happened. So we don't need to do anything. And then I'm going to put an empty vertex at each solid vertex. Okay. And then I'm going to put a solid vertex in each face. And then I'm going to shift the boundary mark points counterclockwise by one tick. So I'm going to by one tick, I should say half a tick, because I move it to the arc in between. And then you just connect the solid vertices with the empty vertices and the boundary points like that. So that gives you a new graph, right? So, and then just forget about the old graph. This is a new graph, okay? And this new graph is guaranteed to have one lower rank. And the reason is actually not too hard to see. So remember, the rank is this kind of average among the zigzags. And during this procedure, what happens is that each zigzag got pushed to the left a little bit, such that the difference all drop by 1. And then when you take the average drop by 1 as well. And that's all the reason that this will give you a one lower rank plabic graph. Okay, so yeah, so this is from the study of amplituhedron. But then we observe that if you keep doing this, the rank drop by 1 every time. So in the end, you're gonna run out. The procedure is going to terminate. So how do you relate these graphs? So we proved that if you start with reduced plabic graph of rank m, and then just keep doing this procedure, then you take the union of all the I forgot this GK here. You take the union of all the graphs that you get, and that graph is a Legendrian weave. And it describes the same cluster structure as the reduced plabic graph that you started with. And we call this a Positroid weave. So let me give you an example. So this was the top cell for Grassmannian 3.6. So you run it once, get this one. And then next time, because of this two valence, you need to get rid of them. So let me get rid of them first. So you get this graph, and then you run it again, right? So you first put the empty vertex, and then you connect them, and then you rotate by half a tick, get this graph. Okay, so note that this is a rank 1 graph. There are no solid vertices whatsoever. Okay, and then you take the union of the blue and the red, you get a weave. Okay. Let me also point out that now you also get a correspondence between the y cycles and the faces, as you should. Right. So this hexavalent first vertex corresponds to this trivalent tree. This square face corresponds to this edge here. This face corresponds to this trivalent tree. This face corresponds to this edge. Right. In particular, the square move that you could perform before now becomes the mutation along this little edge here. Any question? Okay. So what about the flat moduli space? So as I said, the rank 1 local system can be understood as some flat moduli space, but you can actually recover this flat moduli from the positroid using this procedure backward. So what do I mean by that? So start with the lowest weave, right? So it's going to be a reduced plabic graph of rank 1. So you just cut the disk into n many regions, and you can use the rule of the row to associate a line to each region. So it's 1, 2, 3, 4, 5, 6. And then you overlay the next weave, and then in each region, right, you're going to just take the union of the lines below it that gives you a two-dimensional space in each face. So for example, this face arcs over the 1 and the 5. So this is going to span of 1, 5, span of 3, 5, span of 1, 3, and so on. In particular, if you are willing to go one extra step, you actually recover the target labeling of the original thing. So for example, this middle face here, it's the union of this two-dimensional, it's a span of these two-dimensional spaces. So it's going to be a 1, 3, 5 in the middle. So you can also recover this, recover back the target labeling. Okay, so as I said at the very beginning of the talk, the one benefit that we get from here is that you can now mutate along non-square faces. So for example, there's a hexagon face in the middle of this graph. Trying to do reduced plabic graph mutation, you get nowhere. There's no available procedure for you to do it. However, if you do it with weave, you do get something. Right? You can mutate this weave, and mutation tells you get this weave. And in particular, if you use the flat moduli language, there's a canonical way to change it to a flat moduli here, and you can compute monodromies and merodromies very explicitly. So it gives you a very explicit way to compute cluster A and X variables using the flat moduli language. Okay, so I also prepared, so I have some time left, also prepared a non-top cell example. This example is kind of boring from the cluster viewpoint, but let me just show you that this procedure still works if it's non-top cell. So first, you start with this plabic graph. You run it once, you get this one. So notice that if you have a solid lollipop, it gets automatically deleted because solid lollipop is already like 5 goes to 5. So when you goes down one more, it just disappears. Right. So it gets dropped. And then the next one, right, you start with the blue one, get the red one here. You start with the red one, you get the supposed to be the green one, but it doesn't look very green to me. And then you take the union, that's the weave. Right. So now I have some time left to just go through all the results that we can get from this construction. So first, the boundary of this positroid weave is the link. So you can view this Lagrangian surface as an exact Lagrangian filling to the link. So link is a one-dimensional manifold, and then the surface is two-dimensional manifold, but it bounds this one-dimensional manifold. So in other words, right, a Legendrian link lives inside the contact R3, and then the surface lives inside the symplectic R4, and it fills this link. Okay, and there's this Kashiwara-Shapira moduli space. You can decorate it in a certain way to make it totally isomorphic to the positroid strata. This is so this is going to be, so without the decoration, it's just a flat moduli. and then you trivialize the boundary. You trivialize the local system along the boundary, right? Because the positroid is an A variety, you need to decorate the boundary. That's what it is. Okay. Right. So in the joint work, Cassel, Gorski, Lei, Shen Mintao, they use a special family called the Mazur weave to describe cluster structures on Bray varieties. And there's a way to turn these positroid weaves into a Mazur weave. And there's actually not a canonical way, but there's a way for each eye, right? And the way you do it is you run this procedure with a perfect orientation on the reduced plabic graph. Okay. So there's something called perfect orientation developed by Positroid's early work. And if you run it with that, it gives you an orientation on the weave, and just put the weave along that orientation, it gives you a Mazur weave. Another result is that in the joint work Gonchov and Canyon, they construct this conjugate surface, which is the ribbon graph along the reduced plabic graph. And it is known that, well, it's proved in Shunday, Truman, Williams, Zaslow, that this conjugate surface can be seen as an exact Lagrangian in the cotangent bundle of the disk. This iterative T-shift procedure, although it's described combinatorially, it is actually geometrically at a Hamiltonian isotopy from this surface to our exact Lagrangian filling. Another result is about the Donaldson-Thomas transformation, right? So in my work with Roger and also the Bray variety paper, we all consider this Donaldson-Thomas transformation, and geometrically it can be described as a composition of some isotopy on the link together with a contactomorphism that flips it upside down. So this is kind of like a transposition described in the symplectic way. So by comparing this action with the Muller-Speyer twist, we can prove that the Muller-Speyer twist map on the positroid stratum coincides with the quasi-cluster transformation, the Donaldson-Thomas transformation. So the quasi-cluster here, it's some technical thing in cluster theory. What it means is it's not given by a mutation sequence, but a mutation sequence together with a Laurent monomial change by Frozens. Okay, so that's also that. And the direct corollary of this is that the target labeling seed and the source labeling seed are quasi-cluster equivalent, right? So this was a conjecture for a long time, and now it follows from our result, because the target and the source labeling seeds are related by square of the Muller-Speyer twist. And if the Muller-Speyer twist is dt, then the square is also quasi-cluster equivalent. Okay. Recently, De Campo and Moller they introduced a moduli space of linear recurrence with a cluster X structure for each positroid. So this positroid actually can be sort of a mirror, so following this A-X duality is a mirror of the positroid strata. So using our construction, we can also make another decorated version of the flag moduli, and this differently decorated flag moduli is isomorphic to this moduli space of linear recurrence. Okay, and that's it. Thank you.
You have a connection between positroid cells and some geometry, this positroid weave, or what do you call the geometric thing that you're associating with the positroid cell?
Well, positroid cell itself is geometric, right? But there's a flag moduli space. Is that what you're referring to?
Go back on your talk,
I can go back.
Yeah, the Legendrian, Legendrian thing or other.
Are you talking about this space here?
Yeah.
So this is a flag moduli space. So.
And are those flags like positive flags, or there's no positivity constraint on them?
No, because I'm doing it in the algebraic setting. But while all cluster structures have positivity built into it, so you can do positive things, I guess. But I didn't investigate that.
So you mentioned where in your construction of the weaves that you take the disk as the place where you draw the weave, but you can change it for another surface.
Yes.
Have investigated, like, for example, in the case of Grassmannian, you could also replace the disk by other surfaces, but they get parameterization to replace for the Grassmannian.
For Grassmannian, it's always on the disk. I'm not sure what you mean.
Okay, what means that
I mean, if you replace it by other surfaces, you get the higher time Muller space, higher time Muller moduli space. Yeah.
Okay, so but like, well, the question would be, have you studied leaves and other surfaces?
They are ongoing projects. Yes.